All right, it's 11:15. We'll get started. So any questions on the homework? Any comments? Anything before we get started? Everyone's cool? All right, we have a pretty regular week this week. Make sure you do the homework and turn it in. This week is a really good week to start your own review. Check out the problems in the book. You've got time this week. And of course, the exam is next Friday, exact same procedure. So I'll start uploading practice exams, all of that sort of stuff. But I think, we have a good week and a half to get settled on this material. Yes?
Are you going to put solutions to the homework?
Oh, yeah. Did I not put up solution 3 yet?
I don't think so. I looked last night.
Okay. I sent it to the graders, but then I forget to put it up. So I will put up solutions for 3. And of course, you'll get solutions for 4 after you turn it in, and all the usual stuff will be there. Good question. Thanks for reminding me. Stuff happens. Other questions, comments? All right. So far in section 2, we've been talking mostly about free radical polymerization, right? It's an addition polymerization, it's chain growth, and we've developed the kinetic expressions for free radical. And of course, this is just a prototype reaction showing monomer and crosslinker. Remember that we're looking for these carbon-carbon double bonds, and this is a DF equals 2. This is a DF equals 4. And so we've done this a number of times, depending on what the chemistry is. You get branched or cross-linked polymers when you have higher DF than 2 in there. Otherwise, you get all linear polymers in the absence of chain transfer. But if we get some branching, whether they're short chain branches or long chain branches, what might be happening? So say we have all DF2 monomers, and I say, well, the polymer has some long chain branches. What process has occurred? Chain transfer, but specifically, exactly what process is it? Intermolecular chain transfer to polymer. And I'm going to ask you something that's specific, right? If I say, well, we're using DF2 monomers and we have short chain branches, what process has occurred? Intramolecular chain transfer to polymer. Does the molecular weight change when I have chain transfer to polymer? No. Okay, good. Yeah. So these are the things that you're going to have to remember for the exam. I mean, the calculation part, we have some rate laws. We have some things we have to calculate. You need to know the difference between X bar N naught and X bar N. So there is a good amount of calculation, but you also need to be familiar with the concepts. Yes?
Does it matter like what your DF is when it comes to inter or intra?
No. So the DF is separate from inter versus intra. So I brought up intermolecular chain transfer to polymer and intramolecular chain transfer to polymer, because with those processes, you don't necessarily get a linear polymer. Just like this, right? If you have a higher DF, you can get a branch polymer. So now we have a couple different ways to not get linear polymers. But the question will be very specific. I'll say you have a DF of 2 or you have this monomer, this is what the polymer looks like. Or I'll tell you there's a mixture of different monomers, what happens. And so, we mostly assume that the polymer is linear in the absence of other information, but there are ways to get branching, short, long, branch polymers, and of course, cross-linked polymers, depending on the exact situation. Yeah. All right. And so we've been mostly talking about free radical polymers, and we have to remember where those free radical polymers lie: chain growth, addition, and now we're going to move on to ionic polymerization. So you're going to have to know these mechanisms for exam number 2. They follow some of the same rules as free radical because it's still an addition chain growth polymer, but there are some details that are different, and that's what we're going to work on the next couple of lectures. And so if we're talking ionic polymerization, you've got two types of ionic polymerization, cationic and anionic, and it's named just like free radical polymerization, right? We were moving radicals beforehand. That was the active center. So if you see something like this, you know that this one is radical polymerization. And you know what types of initiators you need for radical polymerization, right? What do you need to start a radical polymerization? What has to be the characteristic of the initiator? Has to make radicals, right? And so you need to be looking at the chemical structure of that initiator, or know something like AIBN or benzoyl peroxide, and you say, that's a radical initiator, so I know I'm going to have radical polymerization, because AIBN or benzoyl peroxide can't initiate cationic polymerization or anionic polymerization. So right away, when you see the monomer, a vinyl monomer, right? Okay, it's going to be addition polymerization, and then based on what initiator I have, that gives me clues as to what the mechanism is and how I handle that. So we're going to go through cationic polymerization and anionic polymerization in detail. And I'll tell you that some monomers do different types of polymerizations depending on how they're initiated. So you want to pay attention to that mechanistic detail. All right. And so this is not a clicker question. This is what we did last time. So you know that some monomers are more or less likely to do anionic or cationic polymerization depending on the electronics that stabilize that charge, right? So the key for these mechanisms is for cationic polymerization, you have to stabilize that cation. And so what stabilizes positive charges if we're talking about this X group right here? In order to stabilize positive charge, go ahead. Well, let's say it in words. Yes, so you need an electron donating group with excess electrons to complement the positive charge. You need to have that straight in your head, because you can remember that positive charges on carbon are not common, right? You haven't seen them a lot, even though carbocations are a thing that's used in chemistry. And you can think about that positive charge doesn't really want to be uncompensated or left alone. And so we'll talk about the counter ion that stabilizes that, but an electron donating group will help stabilize that positive charge. You don't want an electron withdrawing group, because that's sucking more electrons away from that cationic center, and that's making it more unstable. And then in anionic polymerization, of course, if we're talking about things that stabilize a negative charge or excess electrons on carbon, that's when you need an electron withdrawing group to help stabilize some of those excess electrons. And of course, you have a countercation floating in solution that compensates that charge as well. And so you want to make sure that you have electron withdrawing, electron donating, cationic, anionic, all sorted out. So if you have it, you can remember it. But if you're unsure as to what we just talked about, that's something to study, something to come to office hours for. But remember, you're trying to stabilize the charge, not add more positive or negative charge to it. Okay. And we covered that in that clicker question. Now, you don't need to memorize this table, but you should take a look at it, especially for things like styrene. You know what styrene is. And it turns out that styrene will do addition polymerization by all three different mechanisms. And so I could say, you're going to polymerize styrene, here's your initiator, and it's up to you to figure out what mechanism of polymerization that is. And I'll say, well, styrene can go by all the mechanisms, you know, based on the clues in the problem. You need to say, oh, that's going to be a cationic polymerization initiator. Now I know what to do. Not all monomers, of course, go by all three mechanisms. we have acrylonitrile here, which of course has that very strong electron withdrawing group on it. And so in general, it's going to go by anionic polymerization because it stabilizes that charge. And I don't know if acrylonitrile is in here. Right here. Here's acrylonitrile. It will do radical. I mean, you can't, it's hard to figure out if it's going to do radical polymerization. You probably either need to assume that it will or be told that it will, but it doesn't do cationic polymerization because of that electron withdrawing group right there. So no cationic polymerization because you can't stabilize that positive charge, but it does anionic just fine. So again, you don't have to remember or memorize this table. You just need to know that different monomers can go by different mechanisms depending on how they're initiated. And if I give you a table like this and ask you a question about it, you need to be able to interpret it. So, you know, I might ask you some question like, which monomers can be initiated by all three mechanisms that we've learned for addition polymerization? And so you say, okay, what's the legend of the table? Check mark means that works. X means it's not going to work, or X parentheses means it might, but not very well. And so I look and see which ones fulfill all the different mechanisms, and it's dienes and styrene. And we're going to talk about dienes in a second. That's the last thing that we're going to do before we take the exam. Any questions on a table like this, or the difference between free radical, cationic, anionic, and what happens when? All right, so just like we went into the details of free radical polymerization, pushing the arrows, figuring out how initiation works, you did that for your homework, we're going to do the same thing for cationic and anionic polymerization now. Okay, so in all addition polymerizations and all chain growth, you need to initiate the active center, right? So you still have initiation for cationic polymerization. Even though the active center is not a radical, we still call it initiation, because otherwise the styrene is just going to sit there and, you know, there's no radicals or anions or cations formed. And so you need an initiator to start the polymerization. And so these initiators tend to look like some strong acids, although HCl and HBr don't work very well, or some of these other funny initiators. And I'll, you know, if it's going to be a strange initiator, I'll tell you it's going to initiate cationic polymerization. Or if you see H2SO4, you're like, ah, I know what that's going to do. And so let's say we have H2SO4 as our initiator. What's R plus and what's A minus in H2SO4? What's the R plus? H plus, that's right. Sulfuric acid is a strong acid, which leaves us with what as A minus? HSO4 minus. Good. No two protons coming off. No 2 minus sulfates there. We're only going to pull one proton off because we want a +1 charge for our cationic initiator. What do protons really like to do? What does H plus really want badly? An electron. In fact, it wants, you know, to share electrons. It wants its own, so it combines with other H pluses to form hydrogen, right? If you have enough electrons around, or it will grab electrons from this double bond. And so that's very interesting. You see this is a full arrow. So you make a covalent bond with the R plus. And if you take away that electron density from this carbon, you've got a full positive charge. Not a radical, not a half arrow. There's not an electron left, an unpaired electron left behind. That's what a radical is. Fully 2 electrons go and bond with our cationic initiator. And that means you have a positive charge on the carbon. And then because positive charges can't really exist by themselves, this anion compensates the positive charge, and it sits there around the cation in the vicinity of. So look at this very closely. This is cationic initiation, which means a cation is the initiating species because you're going to pass that cationic charge to the carbon. And so I know you're not used to drawing cationic charges on carbon very often. It's a little hard to visualize unless you push this double arrow. Remember, this is 2 electrons. So I push 2 electrons over, I form a covalent bond. With my initiator fragment, and then I have charge compensation. Don't forget that part. If you don't put the A- over by the carbocation and you just let that carbocation sit out there, I'm going to ask you, well, what's compensating that positive charge? You need something. Questions on this? All right, that's the, yes.
So A- isn't bonding with the carbon, right?
That's right. It's forming. What sort of intermolecular force do you have when you write the positive charge and the negative charge, and those things are just sort of around? Yes.
Dipoles.
That's not a symbol for a dipole. Everything has dispersion forces. Ionic. So the intermolecular force holding the anion around the cation is some sort of ionic interaction or a coulombic interaction, right? We call it ionic or coulombic for Coulomb's law, counting charges. And so you don't form a covalent bond. It's an ionic bond. And what do we know about ionic bonds? What if we wanted to separate those ionic charges a little bit more? What do we do? Add water or add a polar solvent, right? So we can influence what's going on here by solvent. And we're going to talk about that as we get a little bit deeper into it. But that's why we say that the anion, the A- is around in the vicinity of the cation. It has to compensate the charge because every positive charge needs a negative charge somewhere. But depending on the solvent, it can be further or closer. All right, good. Propagation. So once you've got initiation, here is your growing chain end. We are 100% certain that it's cationic polymerization because the growing chain end is a cation. Just like the growing chain end for free radical polymerization was radical. Easy nomenclature there. And so in order to make a covalent bond with that carbon, in order to add the next monomer, you notice you have to push 2 electrons again in order to form that new covalent bond. You've taken 2 electrons away from carbon, and so all of a sudden you have a new cationic active center. And it's just a really good idea to practice this and practice this. When you go home, just write it out. Make sure you can get all of the atoms in the right places. I think the last unnumbered question on the homework deals with this as well. And so there's no substitute for just writing this out and making sure it's clear in your mind how to push those arrows, and make sure you can get the active center to move 1 monomer over, right? If you're not moving that active center, you're not doing propagation. Yes?
Does the growing chain end also count as a monomer?
No, this is a polymer, right? It's got a little short tail right here. So this guy is a growing polymer. And I didn't put in the whole parentheses n-1 plus n, to increase the molecular weight or increase the degree of polymerization 1 by 1. We know what that is now. If you see those things, you'll know exactly what's happening. This is just shorthand for growing chain end because we had that little polymer fragment there. It's definitely not a monomer because there's no double bonds in this growing chain end, right? This thing can only add to our monomer like this. Is that a tail to tail, head to head, or head to tail addition that we just did? Head to tail, right? This is the head. Most substituted carbon. This is the tail. This is the tail of this monomer. This is the head. And so we did a head to tail addition. Same thing as in free radical. They're named the same. They go in the same way. So head to tail addition is the dominant mechanism of monomer addition in cationic polymerization. Now, the head to head and tail to tail looks the same in the polymer, right? It's going to be a very strange mechanism. We're not going to write it out. But if I just say write a head to head addition in the polymer, you could just write that out because you know what the head is. Doesn't matter how it was polymerized. All right, so that's propagation. And then this is the hard part about cationic polymerization, of course, other than initiation and getting the arrows moving correctly, is that termination and chain transfer are different compared to free radical. So you just need to learn this. And so we'll go through this and it'll actually be clear once we do anionic, because anionic does something completely different. And so being able to separate out free radical termination, cationic termination and chain transfer, and anionic termination will be important. Okay, so we have our growing chain end. And so termination usually occurs by what's called ion pair rearrangement. That's a very fancy name for saying that these two electrons, we push those arrows down, we get a double bond. Great. And we reform our initiator. It's called ion pair rearrangement because nothing's disproportionating. What also is happening in terms of the difference of this termination mechanism. So if I write this equation and say this is a termination mechanism versus free radical, what do we need for free radical termination to happen? Yes. You needed two active centers, right? M dot concentration and M dot concentration had to get together. And so that's a second order reaction because you have concentration of reactants multiplied together. What order of the reaction is this type of termination? First order. You just have one reactant and it terminates. And so it's first order for termination by cationic polymerization. That's really interesting. You notice that you only have double bonds at the chain ends, which means every single chain that's terminated is going to have a double bond. So you don't get a double bond and then a dead chain like you do with free radical polymerization disproportionation, because you move the proton over, you get one with the double bond and one without. Every single chain that's terminated with cationic polymerization has double bonds at the end. And then you get your initiator back, and that can initiate a new chain because we have our H plus and A minus back together again. So write this out. This is the only termination step that we're going to study for cationic polymerization. And so you just need to know that ion pair rearrangement is how cationic polymerization terminates. Yes?
So which is easier to do in terms of energy standpoint, radical or cationic? Does it vary?
I mean, easier from an energy standpoint is a hard thing to answer. I think that free radical polymerization is more common because it's less sensitive to impurities. Cationic polymerization is tricky. There aren't lots of cationic polymerizations except for some key ones. So let's just say that free radical polymerization is more common because it's easier to control. It's a lot more well studied. Cationic polymerization exists, but it's only used in very specific circumstances. All right. We can also have chain transfer. And so you can terminate by chain transfer. And so whether this is a termination reaction or a chain transfer reaction is up to you. I guess we're stopping an end growing chain, and we chain transfer to monomer, and this continues to polymerize. Notice we have our double bond right here again. This probably won't reinitiate because it's got all sorts of R groups around that, and you can't attack this carbon again. So what happens to the overall molecular weight when we have chain transfer to a monomer, like in the bottom line here? What happens to our overall, let me get that going. What happens to our overall X bar N when we chain transfer to monomer? It decreases, right? We're forming new shorter chains, and so the overall X bar N will go down. So when we have increased chain transfer to monomer or solvent or something, same with free radical, the overall degree of polymerization goes down. Okay, so I mean, you have to be a little bit aware of when we say termination versus chain transfer. It's you know, it's tricky because basically we've chain transferred here to initiator, right? And so you're terminating the chain and cationic polymerization, but other things can happen. So this is something that you just need to learn in practice. All right, any questions on that so far? Again, take these home, write them out, figure it out, and you have a homework problem to practice on. And so just what we mentioned before, because the growing chain end is what we can call a contact ion pair, or in some cases, solvent separated ion pair, or free ions. If we move that anionic and cationic charge apart from one another, we get faster propagation because it's a lot easier to slide a monomer in here if the anion and cation are far away from one another than it is here. If the anion and cation are very close together, it's harder to get a monomer in there to propagate. And so we can really change the rate of propagation by changing the solvent. And so we can increase solvent polarity, and you get faster and faster propagation because the anion and cation are bound together with Coulombic forces, right? And so as we raise the polarity, that anion and cation moves away, and you get faster propagation because you can slide the monomer in there and the anion isn't in the way. Okay, so polar solvents help to separate ion pairs, and more ion pair separation actually gives you a reduction in ion pair rearrangement. If you get that anion far away from the chain end, this proton has a hard time finding it, but it really increases the rate of propagation as well. So cationic polymerizations, you really want to control the solvent polarity and get it just right. Questions? Okay, this is a short slide, but it's a key slide, so make sure you remember that one. All right, so that's all we're going to learn about cationic polymerization. It's just a few slides, but remember, it's a different initiation scheme. Propagation, I think you can handle head to tail, moving those 2 electrons instead of 1 electron for free radical. And then you have to remember about termination and chain transfer to monomer. Yes?
Will we have any equations to like solve for rate of propagation, or are they the same as radical?
So it turns out they're mostly the same. We'll go over some of the key kinetic equations, but in general, we're going to use the more complicated expressions for free radical polymerization, because, we can come up with all the variables, right? We know the concentration of the initiator. You have to be told what the initiation efficiency is. You have to know something about the rate of decomposition. So if you look at this mechanism, you can start to figure out which equations make sense and which don't. In general, we'll apply those to free radical polymerization, but there are some key equations that we'll use for cationic and anionic that are coming up. Good question. All right, Now we're going to talk about anionic polymerization, and it's the same story, but instead of propagating a cation, you propagate an anion. And so these are some key monomers for anionic polymerization. And anionic polymerization is special because it's one of the ways that we can make well-defined polymers of exact length. So like I said, cationic polymerization is used in very specific circumstances. It's been studied in the past when they figured out the mechanism, but anionic polymerization is used extensively to make well-defined polymers. Low dispersity. You should all know what low dispersity means. And it's also used to make block polymers, which we'll talk about in a second. We had a slide on block polymers way back on the first or second day of class. I'll remind you what they are. But anionic polymerization is practiced industrially. That's how synthetic rubbers are made in a lot of cases. And so if you have like a little squishy handle on your toothbrush, or like, you know, soft touch, rubbery feeling things, that's usually not natural rubber unless it's a rubber band. It's some sort of synthetic rubber that's probably made using anionic polymerization. All right, so we'll spend some time on anionic polymerization because it's really important. So it's hard to tell if this is a cationic or anionic initiator, right? Because this is just an ionic compound. You get potassium coming off, and you get that NH2 minus. So if it's a proton coming off, H plus, you can probably be sure that it's cationic polymerization, just as we talked about before. Most other things, especially containing potassium, are really good anionic polymerization initiators. And so, you know, I will help you decide which mechanism it is. But for now, we have our initiator. So our initiator has to dissociate. And then we have this really interesting scheme where we initiate on a negative charge on growing chain end. Remember, this is anionic polymerization, and it's named by the identity of the growing chain end. So that's an anion, and then you have your counter cation here. And so in order to make that happen, you basically just have these two electrons make a covalent bond with that carbon, right? Because at the end of that double bond is a carbon, and you kick both of those electrons now onto the head carbon. Why are those electrons, why is that negative charge stable on that carbon? Why doesn't it go the other way? Go ahead. Because the negative charge is stabilized by resonance of that benzene ring or that aromatic ring, right? So we can rearrange all the double bonds. We have excess charge here, but the presence of this stabilizes negative charge on carbon. Just like free radical, right? And so that's why we don't change head to tail nomenclature when we talk about different types of addition polymerizations, because the head, the thing that's where the growing center is going to be, has some stabilization character for the species we're interested in. The tail carbon never has any stabilization, and so it's just sitting out there. It's ignored. Yes?
We're still moving 2 electrons here, right?
Yes. So remember that negative charge, since it's a line, stands for 2 electrons, right? If we just moved 1 electron, what would we have? Well, we have a half arrow, but what do we call that? A radical, right? Yeah. So you could try and move one electron, but then you can't make a covalent bond, or you need to get an electron from the double bond, and then all of a sudden you have a radical out there, not an anion. Yeah. So those are full arrows, just like I wrote them. And so this is why it's worthwhile to sit down and practice. Okay, I'm going to initiate styrene using radical polymerization. I'm going to initiate styrene using cationic polymerization. I'm going to initiate styrene using anionic polymerization, and make sure you can write all those down and know. Good. Any questions on this? So again, this is initiation, same as before. Got to initiate those anions somehow in order to get polymerization to happen. So what if I tell you you have a bunch of styrene and you don't have any polymerization? What are some causes where you cannot have, you're trying to do, let's say you're trying to do a polymerization. So you're mixing stuff up in your lab, you're having fun making polystyrene, and you don't get any polymerization. What might have happened? Go ahead. There could be an inhibitor left. That's a really good answer. Some of these polymerizations, you have to add a bunch of stuff, right? You might have forgotten to put in the initiator as well. So when you don't have any polymerization, either you have forgotten initiator or there's inhibitor in there that's not all the way used up. That's a good answer. All right. Other questions, other comments on this? Okay. So propagation is going to be exactly the same thing as before. So we have our anion right here. And if you look in the book, I think that they don't put the cation in there. And so I put the cations in there just to stabilize the charge. So they're hanging out. So you have your anion. It's going to add 2 electrons. Let me get around this potassium here. 2 electrons to this carbon. That makes a covalent bond with the carbon right there. And then you have an anion active center. Okay. So you can have chain transfer to solvent as well, which means that the growing chain end, this anion comes over here, and we transfer the negative charge, in this case, to that ammonia, which is a solvent. So it plucks off the proton, and we have an anion left, and we have our cation, which of course can reinitiate a polymerization. Okay. The one interesting thing about anionic polymerization, and this is why it's used more often than cationic polymerization, is that there's no formal termination. So we don't have a termination reaction that we can easily write when we have our growing chain end. So if we go CH2, see, let's put the phenyl ring in, and we have our, oh, sorry, that's a CH. And we have our negative charge here. There's not a really easy way to figure out how to terminate that extra, those extra 2 electrons. And so in anionic polymerization, there's no real termination. And so that's cool. This note talks about hydride formation. You'd have to get rid of an H-. That's not going to work very well. There's a bunch of reasons why we don't have termination in this mechanism, but that's what's special about anionic polymerization, and that's why it's used a lot. We're going to talk about what that means. So the type of anionic polymerization that we talk about most often is called living anionic. So if we don't have termination, if you never die or the chain never dies, you're living, right? And so in a lot of cases, this is called living anionic polymerization. And so this initiation right here is not necessarily living, because you can have a lot of chain transfer back to your initiator. But in the scientific literature, there's been a lot of study of living initiators. And this is a complicated initiation scheme. You're not going to be responsible for pushing all the arrows here. But what you need to be responsible for is this is called sodium naphthalide. And what happens with sodium naphthalide is you can really stabilize that radical anion on the naphthalide or the naphthalene rings. And so all you need to know on this slide, or at least one of the main things you need to know on this slide, is that if you want to do living anionic polymerization, you want this sodium naphthalide, which is a type of electron transfer initiator. I think I have a question on that either in the PLAs or in your future work. Electron transfer initiation gives living anionic polymerization. We haven't talked about electron transfer initiation up to now, so this is a special one. And this is why we're going to spend some time with living anionic. So there's various things that happen, and we won't talk about initiation step 2 and radical coupling because that's complicated. But what we will talk about is this really interesting looking molecule, which now has 2 growing anionic active centers. And this is one of the things that if you do living anionic polymerization in the lab with sodium naphthalide, sometimes you forget about this unless you go back and look at the book, is that now you have 2 active centers that are going to propagate each direction. So it's still addition polymerization, it's still chain growth, it's still anionic polymerization, but the special thing about sodium naphthalide is you get these chains growing from each end. So that's a concept where you have electron transfer initiation with sodium naphthalide, gives you living anionic polymerization, and then you get this 2-center propagation on the same chain. Those are just things to remember. All right, you can get out your clickers. And I will start the clickers. You can always get them out at the beginning of class because you'll be sure that we're going to have a clicker question. So CD. Great. All right. How much sodium do you need in order to prepare 1 kilogram of polystyrene with a molar mass of 300,000 grams per mole by anionic polymerization? This is a lot. We just talked about this, right? And so we need to start to think about, okay, what's going on? What do we know about this? So the first thing we know is 300,000 grams per mole. So that's great. What does that usually signal for us? What are we interested in when we know the molecular weight and we know the polymer? We have M0. We have Mn. And how are M0 and Mn usually connected? That's right. So we can figure out what X bar N is. Great. Now knowing that, that means that how many monomers we add per chain, that is what X bar N is, right? And so the question is, how much initiation do you need in order to get that to happen, right? And so now we can figure out, okay, this is my degree of polymerization. I've got a sodium on each side, right? Remember this chain, once we make it a chain, once it propagates, single chain with X bar N requires 2 initiator molecules. Great. And so I'm going to go forward and walk you through the math, and then we'll discuss it. And so the moles of polymer that you have, 1,000 grams of polymer and 300,000 grams per mole. So you have 3 times 10 to the minus 3 moles of polymer, right? And then the moles of sodium needed, since you have a stoichiometry of 2 growing chain ends, you need double that amount of sodium. So you have 1 mole of polymer, and you've got 2 moles of sodium. So this is different than usual radical initiation, right? Because where does the radical fragment end up when we do free radical polymerization? Just usually ends up on one side unless we have termination by combination or something like that. Same with cationic polymerization. We only had that the initiator fragment on one chain end. Oh, let me stop this. And so you have to be told something, or you at least have to know about having these 2 growing chain ends with sodium naphthalide in order to figure this out. And it turns out, in fact, we didn't need X bar N because we could figure out the moles. If we did need X bar N, we would have it easily. All right, any questions or comments on that? All right. So this is the kinetic part that's going to be different now for living anionic polymerization versus free radical versus cationic. Remember, we haven't talked about living radical polymerizations, even though there is something called living radical polymerizations. You'll learn about that in future polymer classes. There is a such thing as living cationic polymerization as well. But for any living polymerization, this is key formula. So this is X bar N, the average, the number average degree of polymerization is the initial monomer concentration that's what the zeros mean, right? Our initial over the initial initiator concentration. And there's a couple things that we have to remember. K equals 2 for electron transfer initiation. So mostly it will be K equals 2 because we're going to do living anionic polymerization. And we need to build in the conversion because we don't necessarily use all the monomer. But now this gives you a way where you can pre-calculate X bar N relatively easily by the ratio of initial concentration of monomer to initial concentration of initiator. Of course, for free radical, we put in all those kinetic constants and we could get an expression for X bar N 0 as well. And X bar N in the presence of chain transfer, this one is special for living. For living anionic polymerization. So the other thing that's really interesting is X bar N is proportional to C, which means if one variable is proportional to the other, you have some sort of line, right? And so we see a signature where if we look at conversion, and if we look at X bar N or molecular weight, if we have a line relating those two, we know we have living polymerization. And this is a signature. This is how you prove that your polymerization is living. You just can't say, well, I'm doing living polymerization. It's all good. Whoops, I need to move that. Looks good on my screen. So if you plot X bar N, or the molecular weight that you're going to measure, versus conversion, you get this straight line, and that's a sign of living polymerization. Remember, free radical addition polymerization, you get that fast rise in molecular weight, then it levels off. Step growth polymerization, you have the slow buildup of molecular weight. So now we have 3 characteristic curves, and let me just give you this one more slide here. Now we have 3 characteristic curves for our buildup of molecular weight. Step, living, and chain. And we have some characteristic equations that tell us about that, right? And so now, if I show you a plot like this and show you some sort of curve, and I say, what type of polymerization is happening? You're able to recognize that, you're able to solve problems around that. So don't forget living polymerization and why it's linear. So I might say, okay, fine, it's a line. Why is it a line? And it's because X bar N is proportional to C. That's why it's a line. Able to recognize it, able to back that up. Any questions or comments? All right, don't forget extended office hours tomorrow because I skipped office hours yesterday, and I'll see you in class on Friday.